The ocean moves in long rhythms that rarely stop. Even during the quietest nights, waves continue crossing the surface of the world. Some travel only short distances before fading into smaller ripples. Others move for thousands of miles through open water, slowly carrying energy from one part of Earth to another. Tonight, this gentle collection of tidal wave facts will move slowly through calm science, quiet oceans, drifting coastlines, and the patient motion of water beneath the moon. A single wave can begin far beyond the horizon and continue traveling long after the weather that formed it has disappeared. In the deep ocean, many large waves are almost invisible from nearby boats because their energy stretches across enormous distances rather than building upward into steep walls of water. And now, the pace becomes softer again. The sea has always moved in patterns that humans could watch but never completely control. Long before satellites or weather stations existed, people noticed the rise and fall of water along shorelines. They noticed beaches changing shape during the day. They noticed rocks disappearing beneath seawater and returning again hours later. Fishing villages learned the timing of tides through memory and repetition. Harbors slowly organized life around these predictable changes. The movement of tides is connected mostly to the gravitational pull of the moon, along with the influence of the sun and the rotation of Earth itself. These forces create steady cycles that continue every day across the planet. Even quiet bays and narrow rivers respond to these distant gravitational effects. The phrase tidal wave has often been used to describe very large ocean waves, although many of these events are technically different from ordinary tides. True tsunamis, for example, are usually caused by underwater earthquakes, landslides, or volcanic activity rather than lunar tides. Still, the image of immense moving water has connected these ideas together for generations. In the deepest parts of the ocean, waves can travel incredibly fast while remaining surprisingly low in height. A tsunami crossing open water may move at the speed of a passenger airplane while rising only a small distance above the sea surface. Ships far from shore sometimes pass over these waves without noticing anything unusual. As waves approach shallow coastal areas, their movement changes. The ocean floor begins slowing the lower portion of the wave while the upper energy continues moving forward. This causes the water to rise higher and compress into a more visible form near land. Many coastlines around the world are shaped slowly by wave energy over thousands or millions of years. Cliffs are worn down grain by grain. Sand shifts from one shore to another. Barrier islands migrate gradually through repeated storms and tidal motion. Some beaches almost disappear during certain seasons before returning again months later. Winter waves often carry sand away from shorelines, while calmer summer water slowly rebuilds them. To a casual observer, the beach may appear permanent, but it is always moving in small ways. The moon's gravity pulls on the oceans continuously. Because Earth rotates beneath this pull, different regions experience changing water levels throughout the day. Most coastal places experience 2 high tides and 2 low tides roughly every 24 hours and 50 minutes. This extra 50 minutes exists because the moon is also moving in its orbit around Earth. Each day, Earth must rotate slightly farther for the same location to align with the moon again. The oceans quietly follow this shifting rhythm. Spring tides occur when the sun, moon, and Earth align during full moons and new moons. Despite the name, spring tides are not connected to the season of spring. The word refers to the idea of water springing outward into stronger tidal ranges. During these periods, high tides become slightly higher and low tides become slightly lower. A week later, neap tides create gentler differences between high and low water levels as the sun and moon pull at different angles. In some places, tidal ranges are very small. The water may rise or fall only a short distance each day. In other regions, especially narrow bays or funnel-shaped coastlines, tides can become dramatic and powerful. The Bay of Fundy in eastern Canada is famous for some of the highest tides on Earth. In certain areas there, the difference between low tide and high tide can exceed 15 meters. Boats resting on the seafloor during low tide may later float high above the same ground. Tidal bores are another unusual ocean phenomenon. These occur when incoming tides push upstream into narrow rivers or estuaries, forming visible moving waves that travel inland. Some tidal bores can continue for many miles. People have surfed tidal bores in rivers around the world. Unlike ordinary ocean surfing, the wave may continue moving steadily for long periods without immediately breaking apart. The Indian Ocean tsunami of 2004 reminded the world how much energy water can carry. That tsunami was triggered by a massive underwater earthquake near Sumatra. The resulting waves crossed entire ocean basins and affected coastlines thousands of miles away. Scientists study seismic activity carefully because underwater earthquakes can displace enormous amounts of water very quickly. When the seafloor suddenly rises or falls, the ocean above it also shifts, beginning long waves that radiate outward across the sea. Modern tsunami warning systems rely on networks of sensors, satellites, and monitoring stations. Some devices rest deep beneath the ocean surface and measure pressure changes caused by passing waves. These systems help provide advanced warnings for vulnerable coastlines. Even with advanced technology, the ocean still contains many mysteries. Deep water remains difficult to study because pressure increases enormously with depth. Sunlight fades rapidly beneath the surface, leaving most of the ocean in darkness. Internal waves also move through the ocean beneath the visible surface. These underwater waves travel between layers of different water density. Some internal waves can become much larger than ordinary surface waves, although they remain hidden below. Satellite images have occasionally revealed enormous internal wave patterns stretching across the sea. These formations resemble soft ripples in clouds or sand dunes viewed from above. The Pacific Ocean contains many regions where tsunamis are more likely because tectonic plates meet beneath the water. This area is often called the Ring of Fire due to frequent earthquakes and volcanic activity around its edges. Volcanic eruptions beneath the sea can also generate waves. When underwater volcanoes collapse or explode, they may suddenly displace water and create tsunami events. Landslides entering the ocean can produce similar effects. In 1958, a giant wave occurred in Lituya Bay, Alaska, after a massive landslide crashed into the water. The resulting surge reached an extraordinary height against nearby cliffs. Trees were stripped from the landscape far above the bay. Although this event is often described as a megatsunami, it happened within a narrow enclosed area rather than across an entire ocean basin. The word tsunami comes from Japanese and means harbor wave. The term became widely adopted internationally because ordinary labels like tidal wave did not accurately describe the scientific cause of these events. Many animals appear sensitive to changing ocean conditions. Some marine species react to pressure shifts, vibrations, or unusual water movement before humans notice obvious changes. researchers continue studying how animals perceive environmental signals. Sea turtles spend much of their lives crossing enormous ocean distances. They navigate using Earth's magnetic field along with other environmental cues. Some return to the same beaches where they hatched decades earlier. Whales also travel through oceans along seasonal migration routes. Certain species communicate using low-frequency sounds that can travel remarkable distances underwater. The ocean carries sound differently than air, allowing calls to move across huge spaces. The deep ocean is often colder than people imagine. Even in tropical regions, temperatures far below the surface can approach near freezing conditions. Cold, dense water circulates slowly through global ocean currents over long timescales. Ocean currents influence weather patterns around the planet. Warm currents transport heat toward colder regions, while cold currents help regulate temperatures elsewhere. These slow-moving systems interact continuously with winds, tides, and Earth's rotation. The Gulf Stream carries warm water across the Atlantic Ocean and affects climates far from its origin. Without these large-scale ocean movements, many regions would experience very different weather conditions. Waves themselves mostly transfer energy rather than transporting large amounts of water across oceans. A floating object in deep water often moves in gentle circles as waves pass beneath it instead of traveling long distances with the wave. This circular movement becomes weaker deeper below the surface. Far enough down, wave motion almost disappears entirely. Storm surges are different from tsunamis but can still produce dangerous coastal flooding. Strong winds and low atmospheric pressure during hurricanes or cyclones push seawater toward land. Combined with high tides, storm surges can raise coastal water levels dramatically. Some of the deadliest ocean flooding events in history involved storm surges rather than seismic tsunamis. Low-lying coastlines are especially vulnerable during powerful tropical storms. Mangrove forests can help reduce wave energy along certain tropical coastlines. Their dense root systems slow moving water and trap sediment over time. Coral reefs also absorb part of the energy from incoming waves before they reach shore. Coral reefs themselves are built slowly by countless tiny organisms called coral polyps. Over long periods, these living structures create vast underwater formations visible even from space. The sound of waves reaching shore is partly created by collapsing bubbles in the water. When waves break, trapped air compresses and releases energy, producing the familiar rushing sound associated with coastlines. Pebble beaches sound different from sandy beaches because the water moves stones against one another during each wave cycle. Some shores produce soft rattling sounds as waves pull pebbles backward into the sea. Moonlight reflecting across ocean water creates shifting patterns because waves continuously alter the angles of the surface. Even small ripples can scatter light into long shimmering paths. Bioluminescent organisms sometimes cause coastlines to glow blue at night when waves disturb the water. These tiny marine creatures produce light through chemical reactions inside their bodies. In calm darkness, moving waves may appear softly illuminated. Some ancient cultures believed tides were connected to breathing oceans or sleeping sea spirits. Before gravity was understood scientifically, the rhythmic rise and fall of water inspired many explanations rooted in mythology and observation. The scientific understanding of tides developed gradually over centuries. Astronomers and mathematicians studied the relationship between lunar motion and ocean patterns. Over time, measurements confirmed consistent connections between celestial mechanics and tidal behavior. Isaac Newton's theory of gravity helped explain why tides occur. His work described how massive objects attract one another, including the gravitational interaction between Earth, the Moon, and the Sun. Even today, predicting tides precisely remains complicated because coastlines, underwater geography, wind, and weather all influence local conditions. Computer models now process enormous amounts of data to improve forecasts. In narrow channels, tidal currents can become extremely fast. Water forced through tight spaces accelerates and forms swirling turbulence. Some regions experience powerful whirlpools created by these conditions. The maelstrom near Norway became famous in literature and folklore because of its strong tidal currents. Stories once exaggerated its power into enormous mythical whirlpools capable of swallowing entire ships. Oceanographers use specialized instruments to measure wave height, salinity, temperature, and currents. Research vessels travel through difficult conditions to collect information about the changing sea. Satellites now monitor sea surface height across the planet with remarkable precision. These measurements help scientists track ocean circulation, climate changes, and rising sea levels. Sea level itself is not perfectly uniform around the world. Gravity, temperature, currents, and Earth's shape all influence regional water levels slightly differently. Glacier and ice sheets store vast amounts of frozen water. When global temperatures rise, melting ice contributes gradually to sea level increase. Warmer seawater also expands slightly, adding further rise over time. Tiny plankton drifting in ocean water produce much of the oxygen in Earth's atmosphere. Though nearly invisible individually, these microscopic organisms collectively influence the entire planet. The open ocean may appear empty from above, yet countless living organisms move through its depths. Many species remain undiscovered because deep ocean exploration is difficult and expensive. Some deep-sea fish generate their own light through bioluminescence. Others survive under pressures that would crush ordinary surface equipment. Hydrothermal vents on the ocean floor release mineral-rich water heated by volcanic activity beneath Earth's crust. Entire ecosystems survive around these vents without sunlight, relying instead on chemical energy. Waves generated by distant storms can arrive on calm shores days later. Surfers sometimes watch forecasts that track swells traveling across entire oceans from weather systems thousands of miles away. Long-period swells tend to feel smoother and more organized than shorter chaotic waves. These rolling patterns can continue arriving steadily even after local winds disappear. The ocean absorbs and stores large amounts of solar heat. Because water changes temperature more slowly than land, coastal climates are often milder than inland regions. Fog commonly forms where cold ocean currents meet warmer air. Tiny suspended droplets create soft gray landscapes along certain coastlines during calm mornings. Sailors once relied heavily on reading tides and currents before modern navigation systems existed. Knowledge of local waters could determine whether ships entered harbors safely or became stranded. Certain harbors are accessible only during higher tides because shallow entrances prevent passage during low water periods. Tidal timing still matters greatly for shipping in some regions. Barnacles attach themselves permanently to rocks, piers, and ship hulls within tidal zones. These small marine animals survive alternating periods underwater and exposed to air. Tide pools create miniature ecosystems along rocky shores. As tides retreat, Small pockets of seawater remain trapped among rocks, supporting fish, crabs, sea stars, and algae. Sea stars move using hundreds of tiny tube feet powered by hydraulic pressure. Although they appear slow, they are highly adapted to life within shifting tidal environments. Some crabs synchronize behaviors with lunar and tidal cycles. Certain species release eggs during specific tidal conditions that improve survival chances for offspring. The Moon gradually moves farther from Earth every year by a very small amount. This slow drift slightly affects tidal behavior over extremely long timescales. Billions of years ago, tides may have been much stronger when the Moon orbited closer to Earth. Ancient coastlines likely experienced different patterns from those seen today. Earth's rotation is also slowing very gradually due partly to tidal friction. The interaction between oceans and the Moon transfers small amounts of rotational energy over time. Days on ancient Earth were shorter than modern 24-hour days. Geological evidence suggests that hundreds of millions of years ago, Earth rotated faster than it does now. The color of ocean water changes depending on depth, sunlight, sediment, and microscopic life. Pure water absorbs red wavelengths more strongly, leaving blue light scattered back toward observers. Near coastlines, suspended sand and algae often create green or brown tones instead of deep blue. Underwater sound travels efficiently because water molecules are packed closely together compared to air. Whale songs, submarine communications, and seismic signals can move across great distances through the sea. The deepest known part of the ocean is the Challenger Deep within the Mariana Trench. Its depth exceeds 11 kilometers below sea level. Pressure there is immense enough to challenge even specialized exploration vehicles. Only a small number of humans have descended to such depths. Much of the deep ocean remains less explored than parts of the Moon's surface. Some waves called rogue waves appear unexpectedly larger than surrounding seas. These rare formations may result from multiple wave systems combining energy in particular ways. Sailors historically described enormous waves that seemed impossible until modern measurements confirmed that rogue waves do occur. Far from shore, the surface of the ocean sometimes appears almost motionless beneath cloudy skies. Yet below that calm appearance, layers of water continue moving slowly in different directions, carrying heat, nutrients, and drifting life across the planet. Ocean water is never completely still. Even in quiet conditions, tiny ripples form from faint winds, temperature changes, or distant movement elsewhere at sea. The surface constantly shifts in patterns too subtle to notice individually. Wave shapes depend on many conditions at once. Wind speed, wind duration, water depth, and the distance wind travels across open water all influence the final form of waves. A long stretch of uninterrupted ocean allows waves to gather more energy over time. This uninterrupted distance is called fetch. Large storms moving across long fetches can produce powerful swells that continue traveling long after the original storm weakens. The Southern Ocean surrounding Antarctica contains some of the longest uninterrupted fetch on Earth. Strong winds circle the planet there with relatively little land to interrupt them. As a result, enormous swells often form and travel outward into other oceans. Icebergs drifting through polar seas also interact with waves. Large ocean swells can flex the edges of floating ice, gradually contributing to cracks and fragmentation over long periods. Sea ice itself changes how waves move through polar regions. Dense ice coverage absorbs and dampens wave energy, creating quieter water conditions beneath frozen surfaces. During storms, waves rarely move in perfectly ordered lines. Different wave systems intersect and overlap, creating complex patterns across the sea surface. From above, these interactions sometimes resemble shifting woven textures. The study of waves is called wave mechanics. Scientists use mathematics and observation to understand how energy moves through water under changing conditions. Some wave energy travels thousands of miles with surprisingly little loss. Because the open ocean offers relatively little resistance, long swells may continue moving steadily across entire basins. Ocean buoys anchored far offshore measure passing waves continuously. These floating instruments record height, direction, temperature, and pressure while transmitting information back to researchers and forecasting systems. Modern surfers, sailors, and coastal communities rely heavily on buoy data for wave predictions and storm awareness. Many underwater earthquakes occur too deep beneath the ocean to create major tsunamis. The amount of water displaced matters greatly in determining whether a destructive wave forms. The shape of the seafloor also affects tsunami behavior. Underwater ridges, trenches, and continental shelves can redirect or amplify wave energy in complicated ways. As tsunami waves enter shallow coastal regions, the distance between wave crests decreases while height increases. This process is called shoaling. Unlike ordinary breaking surf waves, tsunamis often arrive as rapidly rising water levels or powerful surges rather than curling waves. The first sign may be an unusual retreat of water away from shore. In some historic tsunami events, coastlines temporarily exposed large areas of seafloor before the main surge arrived. Fish, rocks, and coral became visible where seawater normally covered them. Many traditional coastal communities developed oral histories describing unusual ocean behavior associated with tsunami danger. These stories helped preserve survival knowledge across generations before written warning systems existed. In parts of the Pacific Northwest, indigenous histories describe earthquakes and ocean surges that modern geology later confirmed through sediment evidence and tree ring analysis. Sand layers deposited inland by ancient tsunamis allow scientists to study events that happened centuries ago. These deposits sometimes reveal patterns of repeated large waves over long timescales. Coral growth rings also preserve information about changing ocean conditions. Like tree rings, coral structures can record environmental patterns year after year. The ocean reflects sunlight differently depending on wave angle and cloud cover. At sunrise or sunset, low light often creates long metallic reflections across moving water. During calm evenings, small ripples may produce delicate overlapping patterns that seem almost geometric. The physics of waves often creates natural symmetry without deliberate design. In enclosed seas or lakes, standing waves called seiches can form when water oscillates back and forth after disturbances such as earthquakes or strong winds. These movements resemble water sloshing slowly inside a bowl. Harbors sometimes amplify certain wave frequencies naturally. If incoming wave timing matches the harbor's shape and dimensions, resonance effects may increase water motion inside the basin. Ancient mariners noticed unusual rhythms in particular harbors long before the physics behind resonance became understood. The Mediterranean Sea experiences tides that are generally smaller than those in many Atlantic regions because of its limited connection to the wider ocean. Some inland seas also experience subtle tidal movement despite being partially enclosed by land. Gravity acts on all large bodies of water, though local geography influences the visible result. The gravitational pull creating tides affects Earth itself slightly. Solid land rises and falls by small amounts in response to lunar gravity, though these movements are far less noticeable than ocean tides. Even the atmosphere experiences tidal effects. Air pressure changes slightly in response to solar heating and gravitational forces. Clouds forming above the ocean often reflect the structure of winds below them. Satellite images can reveal enormous spiral storm systems stretching across thousands of kilometers. Tropical cyclones draw energy from warm ocean water. As moist air rises and cools, heat is released into the atmosphere, strengthening the storm's circulation. Storm waves generated by powerful cyclones can reshape coastlines overnight. Sand dunes collapse, beaches narrow, and tidal inlets shift position under intense water movement. Barrier islands serve as natural protective structures along many coastlines. These long, narrow islands absorb wave energy before it reaches mainland shores. Yet barrier islands themselves are temporary on geological timescales. They slowly migrate under the influence of storms, currents, and changing sea levels. Some islands visible today may disappear naturally over future centuries, while new ones gradually form elsewhere. Ocean sediment settles slowly through water like underwater snowfall. Tiny particles from rivers, volcanic ash, dead organisms, and dust drift downward continuously into deeper layers. Over immense spans of time, these sediments create records of changing climates and ocean conditions. Scientists extract cylindrical cores from the seafloor to study these ancient layers. Microscopic fossils found in sediment cores reveal information about ocean temperatures from long ago. Different species thrived under different environmental conditions. The ocean floor itself is younger than many continental rocks because tectonic plates constantly recycle seafloor material through spreading and subduction. At mid-ocean ridges, molten rock rises from beneath Earth's crust and cools into new seafloor. These underwater mountain chains stretch across the globe. Hydrophones placed underwater can detect distant earthquakes, whale calls, ship traffic, and even cracking icebergs. Sound becomes an important tool for studying environments hidden beneath the surface. During World War II and the decades afterward, oceanographic research expanded significantly because underwater acoustics became strategically important. Today, scientists use many of these technologies for peaceful research into climate, marine biology, and geology. Phytoplankton drifting near the ocean surface responds strongly to sunlight availability. Large blooms sometimes become visible from space as swirling colored patterns in the water. These microscopic organisms form the foundation of many marine food webs. Tiny creatures feed on plankton, larger fish feed on them, and the chain continues upward through ocean ecosystems. The gentle rocking motion felt on boats comes from waves passing beneath the vessel. Different wave directions can create complex rolling movements that experienced sailors learn to anticipate. Large ships are designed carefully to handle wave stress across long voyages. Hull shapes influence stability, fuel efficiency, and motion during rough seas. Lighthouses historically helped sailors navigate dangerous coastlines where hidden rocks and wave conditions threatened ships. Many were built in isolated places constantly exposed to storms and salt spray. Foghorns became essential in areas where visibility frequently disappeared beneath coastal mist. Low-frequency sounds could travel farther through dense fog than light from lamps alone. Some coastlines produce unusual sounds associated with waves and geology. Booming noises may occur when air compresses inside sea caves as waves force water inward. Singing sand beaches also exist in certain regions. Under specific conditions, dry sand grains rubbing together create soft humming or squeaking sounds. Tidal flats exposed during low tide provide feeding grounds for migratory birds. Mud rich with small organisms becomes temporarily accessible before returning beneath water again. The rhythm of tide shapes the daily lives of many coastal species. Crabs emerge during certain water levels. Fish enter estuaries during incoming tides. Birds time feeding activity around exposed shorelines. Some fish species use tides almost like moving highways, conserving energy by drifting with favorable currents. Eels undertake remarkable migrations between rivers and distant ocean spawning grounds. For much of human history, scientists did not fully understand where eels reproduced because their life cycle remained hidden far offshore. Moon phases continue influencing human awareness of tides even in modern cities far from the sea. Full moons often appear brighter when reflected across open water because waves scatter the light continuously. Ancient calendars were closely tied to lunar cycles because the moon provided a reliable visible pattern in the sky. The relationship between tides and the moon is strong enough that some marine organisms synchronize reproduction with lunar timing. Coral spawning events in certain regions occur according to moon phases and seasonal temperature conditions. At night, calm seas sometimes reflect stars with surprising clarity when winds remain weak. Slight ripples stretch reflections into moving lines of light across the darkness. Ocean horizons appear curved very subtly due to Earth's shape, though the curvature becomes more obvious from higher elevations. On exceptionally clear days, distant ships may seem to float above the horizon because atmospheric refraction bends light slightly. Mirages over water occur when layers of air with different temperatures alter the path of light. These optical effects can distort coastlines or create hovering images near the horizon. Before accurate clocks existed, determining longitude at sea was extremely difficult. Sailors could estimate latitude using stars, but east-west position required precise timekeeping. Marine chronometers eventually improved navigation and reduced the dangers of long-distance sea travel. Some underwater mountains rise thousands of meters from the seafloor without reaching the surface. These seamounts influence currents and provide habitats for marine life. Currents flowing around seamounts often carry nutrients upward, supporting concentrations of fish and other organisms. Kelp forests grow in cold, nutrient-rich coastal waters where sunlight still reaches the seafloor. These underwater forests sway continuously with wave motion and currents. Sea otters floating among kelp sometimes wrap themselves loosely in the plants to avoid drifting away while resting. The pressure beneath waves changes rhythmically as water moves. Certain marine animals can detect these pressure changes with great sensitivity. Sharks possess specialized sensory organs capable of detecting weak electrical fields produced by living creatures in the water. Dolphins use echolocation by producing sound pulses and interpreting returning echoes. This ability allows them to navigate and hunt even in dark or murky conditions. The ocean contains rivers within itself formed by differences in salinity and temperature. These water masses flow slowly through one another in layered circulation systems. Dense cold water tends to sink while warmer water remains nearer the surface. This process helps drive global thermohaline circulation across enormous distances. Some scientists describe this circulation as a planetary conveyor belt moving water through oceans over centuries. Underwater canyons cut into continental shelves guide sediment and currents toward deeper regions. Some rival the scale of large land canyons. Submarine landslides occurring within these canyons can occasionally trigger local tsunamis if enough sediment shifts suddenly. The energy released during large earthquakes is difficult to imagine directly. When this energy transfers into ocean water, waves can spread outward silently across entire seas. Tsunamis in deep water often have wavelengths hundreds of kilometers long. A single wave may take many minutes to pass beneath a location completely. Because the energy extends through the full depth of the ocean, tsunamis behave differently from ordinary wind-driven surface waves. The interaction between ocean and atmosphere influences climate systems such as El Niño and La Niña. Changes in Pacific Ocean temperatures affect rainfall, storms, and seasonal conditions across many regions of the world. Fishermen along South American coasts noticed these warming events centuries ago before scientists formally studied them. Warm water expanding across parts of the Pacific can reduce nutrient-rich upwelling, affecting marine ecosystems and fishing conditions. Upwelling occurs when winds and currents bring deep, cold, nutrient-rich water toward the surface. These areas often support abundant marine life. Some of the world's richest fisheries exist near major upwelling zones because plankton growth increases where nutrients reach sunlight. Ocean trenches mark places where tectonic plates descend beneath one another. These regions are associated with many strong earthquakes capable of generating tsunamis. The Pacific Plate moves slowly each year, though the distances are small enough to notice only through precise measurements over time. Continents themselves drift gradually across Earth's surface. The positions of oceans and coastlines today differ greatly from those of ancient Earth. Hundreds of millions of years ago, entirely different ocean basins existed where land now stands. The Atlantic Ocean continues widening slowly because of seafloor spreading along the mid-Atlantic ridge. Salt dissolved in ocean water mostly comes from rocks weathering on land over immense periods. Rivers carry minerals toward the sea continuously. Evaporation removes water but leaves dissolved salts behind, gradually concentrating minerals in the oceans. Different seas contain different salinity levels depending on climate, evaporation, and freshwater input. The Dead Sea, despite its name, is actually a salt lake with extremely high salinity. Its dense water allows people to float easily near the surface. Ordinary seawater also increases buoyancy compared to freshwater because dissolved salts make the water denser. During calm mornings, layers of warm and cool water sometimes separate sharply enough to create visible shimmering boundaries beneath the surface. Divers occasionally notice these thermoclines as sudden temperature changes while descending. Ocean exploration vehicles must withstand crushing pressures at great depths. Even small structural weaknesses can become dangerous under such extreme conditions. Some deep-sea organisms survive without sunlight entirely, relying on chemical energy from hydrothermal vents or organic material sinking from above. Marine snow is the slow, continuous fall of tiny organic particles drifting downward through deep water. Jellyfish have existed in Earth's oceans for hundreds of millions of years. Their simple drifting forms move with currents and pulses of water. Some jellyfish species are nearly transparent, making them difficult to see beneath the surface. Comb jellies produce shimmering rainbow effects as light scatters across tiny moving structures along their bodies. The ocean at night can feel especially vast because visual reference points disappear into darkness. Waves continue moving invisibly beneath the stars, guided by winds, gravity, and distant storms. In many coastal places, the sound of waves becomes part of daily life so completely that people stop consciously noticing it. The repeating motion blends into the background like steady breathing or distant rain. Wave patterns rarely repeat in exactly the same way twice. Even under stable conditions, small variations in wind and current create endless differences in timing and shape. Scientists describe complex sea states statistically because tracking every individual wave directly becomes impossible across large areas. Instead, average wave heights and energy distributions help describe ocean conditions. A calm sea can still contain long rolling swells generated by storms far beyond the horizon. People standing on shore may see smooth rising and falling water beneath otherwise peaceful skies. Sometimes two different swell systems arrive together from separate storms. The crossing wave patterns create diamond-like textures across the surface known as interference patterns. The mathematics of wave interference applies not only to water but also to sound, light, and other forms of energy movement. Nature often repeats similar principles in different forms. The color of foam on breaking waves comes from countless tiny bubbles scattering sunlight. When air mixes into turbulent water, the trapped bubbles reflect light in many directions. Sea foam can gather in thick lines along beaches after storms because waves concentrate organic material naturally within certain water movements. Driftwood floating at sea may travel remarkable distances through currents over many years. Pieces of wood from one coastline sometimes wash ashore on entirely different continents or islands. Messages in bottles occasionally survive long ocean journeys as well, carried slowly by currents and tides. Ocean currents helped shape historical exploration routes. Sailing ships often depended heavily on prevailing winds and known current systems to shorten voyages. The trade winds and major ocean gyres created pathways that navigators gradually learned through observation and experience. A gyre is a large rotating ocean current system influenced by Earth's rotation and continental boundaries. There are several major gyres circulating through the Atlantic, Pacific, and Indian Oceans. Floating debris often accumulates within these slowly rotating systems because currents trap material over time. Seaweed drifting through open water creates temporary habitats for fish, crabs, and small marine creatures. Even isolated floating objects can become miniature ecosystems in the ocean. Barnacles attaching to drifting debris reveal how life spreads gradually across marine environments. Tidal estuaries form where freshwater rivers meet seawater from the ocean. These regions experience constantly changing salinity levels as tides move inland and rivers flow outward. Many young fish species use estuaries as sheltered nursery areas before moving into deeper ocean environments. Salt marshes along tidal coastlines absorb floodwaters and stabilize sediments through dense plant growth. Their grasses bend gently with changing water levels throughout the day. The smell associated with oceans partly comes from compounds released by marine organisms and decaying plant material. Sea air contains microscopic particles carried upward from breaking waves. During storms, strong wave action can send salty moisture far inland. Buildings, plants, and roads near coastlines gradually weather under constant exposure to sea spray. Cliffs facing the ocean slowly erode under repeated wave impact. Tiny fractures expand over time until sections collapse into the sea below. Sea arches and sea stacks form when waves wear away softer rock while harder sections remain standing temporarily. Eventually, these formations also continue eroding and changing shape. Caves carved by waves often amplify sound because of their enclosed geometry. Incoming water compresses trapped air and creates deep echoing tones. On calm nights, some beaches produce a faint glowing effect caused by microscopic bioluminescent plankton disturbed by waves. Each movement in the water briefly triggers soft blue light. Ancient sailors sometimes described glowing wakes behind ships as mysterious ocean fire. Today the phenomenon is understood scientifically, though it still appears quiet and unusual in darkness. Many marine organisms use bioluminescence for camouflage, communication, or defense. Some create sudden flashes to confuse predators in deep water where sunlight never reaches. The ocean absorbs different colors of light at different depths. Red disappears first, followed gradually by orange and yellow, leaving blue light penetrating deepest. Divers descending underwater notice colors fading progressively unless artificial lights restore the missing wavelengths. Pressure increases rapidly beneath the sea surface. At only 10 meters underwater, pressure already doubles compared to conditions at sea level. Deep sea animals possess bodies adapted to these extreme conditions. Some would not survive near the surface because rapid pressure changes damage their tissues. Submarines exploring deep oceans must balance strength with buoyancy. Their structures are engineered carefully to resist immense surrounding forces. The first successful deep ocean descents revealed that life existed even in places once thought too extreme to support organisms. Tiny amphipods, worms, and strange fish inhabit trenches far below sunlight, surviving in cold darkness. Ocean trenches also trap sediments over long periods, preserving records of earthquakes, volcanic eruptions, and changing climates. Some underwater earthquakes trigger only small local waves, while others produce basin-wide tsunamis. The exact outcome depends on depth, movement type, and how much seafloor shifts vertically. Strike-slip earthquakes, where plates slide horizontally past one another, usually displace less water than vertical fault movements. The Pacific Ocean is large enough that tsunamis may travel for many hours before reaching distant coastlines. Warning systems therefore rely heavily on rapid detection and communication. Deep ocean tsunami sensors detect pressure changes even when surface height differences remain small. A passing tsunami slightly compresses the water column above the instrument. Computer models simulate how waves will interact with coastlines based on underwater terrain and shoreline shape. Certain bays naturally focus wave energy, increasing local water heights during tsunami events. Others provide partial protection because of offshore geography. Historical records from Japan document tsunamis over many centuries. Careful written observations helped scientists understand recurrence patterns and coastal vulnerability. Stone markers placed in some Japanese villages warned future generations not to build homes below certain elevations because earlier tsunamis had reached those areas. The ocean also experiences quieter long-term rhythms connected to climate cycles lasting years or decades. The Pacific Decadal Oscillation and Atlantic Multidecadal Oscillation influence ocean temperatures and atmospheric conditions over extended periods. Marine heat waves occur when ocean regions remain unusually warm for prolonged times. These events can affect coral reefs, fisheries, and weather systems. Coral bleaching happens when stressed corals expel symbiotic algae living within their tissues. Without these algae, reefs lose much of their color and energy source. Healthy coral reefs reduce coastal erosion by absorbing incoming wave energy before it reaches shorelines. Many reef systems formed gradually over thousands of years through continuous coral growth and sediment accumulation. Atolls are ring-shaped coral islands surrounding lagoons. They often form around sinking volcanic islands as coral continues growing upward toward sunlight. Charles Darwin studied atolls during the voyage of the HMS Beagle and proposed explanations for their formation long before plate tectonics became fully understood. The surface tension of water influences tiny ripples on calm seas. Small insects can even walk across water because surface tension creates a delicate supporting layer. Raindrops striking oceans produce circular waves that spread outward briefly before merging with surrounding movement. During light rain, the sea surface becomes covered with countless overlapping rings that vanish almost immediately. Heavy rainfall can flatten smaller wind waves temporarily by disrupting the transfer of energy from air to water. The smell after rain near the coast combines ocean air with compounds released from soil and plants inland. Lightning striking oceans heat surrounding water and air extremely rapidly, producing thunder through explosive expansion. Despite the enormous size of oceans, most marine life concentrates relatively near coastlines or within sunlit upper layers where nutrients and light remain available. The deep open ocean can appear sparse compared to productive coastal ecosystems. Continental shelves beneath shallow coastal water support rich fisheries because sunlight reaches the seafloor and nutrients circulate efficiently. Kelp forests, coral reefs, and seagrass meadows all thrive mainly in these shallower marine regions. Seagrass beds help stabilize sediments and provide habitat for many small marine species. They also store significant amounts of carbon within coastal ecosystems. The tide line visible on beaches marks changing water levels over time. Seaweed, shells, and debris often gather along these temporary boundaries. Beach sand itself usually consists of tiny fragments of rock, shells, coral, or volcanic material worn down through long erosion. White tropical beaches often contain large amounts of broken coral and shell particles rich in calcium carbonate. Black sand beaches form near volcanic regions where dark minerals dominate the sediment. Green sand beaches exist in rare places where specific volcanic crystals accumulate through wave sorting. Every grain of sand carries a geological history shaped by rivers, erosion, waves, and time. Wave refraction bends incoming waves as they approach shorelines unevenly. Parts of the wave entering shallow water first slow down earlier, causing the wave to curve. This process helps explain why waves often align parallel to beaches before breaking. Headlands extending into the sea receive concentrated wave energy because refraction bends waves toward them. Nearby bays often experience calmer conditions. Longshore currents move sand gradually along coastlines. Over months and years, these currents reshape beaches continuously. Jetties and harbors sometimes interrupt this natural sediment movement, causing erosion in some areas and sand accumulation in others. The moon not only affects tides but also slightly stabilizes Earth's rotational tilt over long timescales. This stability influences long-term climate patterns. Without the moon, Earth's axial tilt might vary more dramatically, potentially altering seasons over geological history. The moon itself likely formed after a massive collision early in Earth's history. Debris from that impact eventually combined into the satellite visible today. Ancient tides may have played roles in the development of early coastal ecosystems billions of years ago. Tidal pools exposed repeatedly to wet and dry cycles created environments unlike either deep ocean or dry land completely. Some scientists believe these fluctuating environments may have influenced chemical processes important in the early history of life. The ocean floor contains mountain ranges longer than any on land. Most remain hidden beneath water, unknown to ordinary observation. Volcanoes beneath the ocean continuously reshape seafloor landscapes through eruptions and lava flows. Pillow lava forms underwater when molten rock cools rapidly against seawater, creating rounded shapes. Hydrothermal vent communities survive using chemosynthesis rather than photosynthesis. Bacteria there obtain energy from chemicals released by Earth's interior. Tube worms near vents can grow surprisingly large despite existing in complete darkness. Marine snow drifting downward from upper waters provides another important food source for deep ocean ecosystems. Dead plankton, tiny shell fragments, and organic particles sink slowly through the water column like gentle underwater snowfall. Whale falls create temporary deep-sea ecosystems when large whale bodies sink to the ocean floor after death. Many organisms gather around these nutrient-rich remains for years. The ocean contains dissolved gold, though in concentrations far too low for practical extraction with current methods. Salt water conducts electricity because dissolved ions carry electrical charge. This property influences underwater communications and scientific measurements. Oceanographers sometimes deploy drifting instruments that move with currents while transmitting data by satellite. These drifting buoys help map large-scale circulation patterns across oceans. Satellite altimeters measure sea surface height differences smaller than many ordinary waves. Such precision helps scientists track subtle changes in ocean behavior. Sea level rise occurs unevenly because currents, gravity, and land movement vary regionally. Some coastal areas sink gradually due to sediment compaction or groundwater extraction, increasing flood vulnerability further. Tidal flooding now affects certain coastal cities more frequently during high tides than in previous decades. Even small increases in sea level can noticeably expand flood reach during storms or unusually high tides. The interaction between human settlements and coastlines has always involved adaptation to changing water conditions. Harbors require continuous dredging in some places because sediment carried by tides and rivers gradually fills navigation channels. Lighthouses once depended on keepers who maintained lamps through isolated nights beside rough seas. Many lighthouse beams rotated using clockwork systems driven by descending weights. Fresnel lenses used in lighthouses concentrated light efficiently through carefully shaped glass sections. Fog sometimes bends sound over long distances above cold water. Ship horns may seem strangely distant or directionless under these conditions. Before radar and satellite navigation, storms at sea often arrived with little warning. Experienced sailors learned to interpret clouds, swells, pressure changes, and wind shifts as early signs of changing weather. A distant storm can send long smooth swells toward shore even before local skies begin changing. These swells arrive silently, carrying energy generated far beyond visible horizons. The ocean continues moving through the dark in slow and patient rhythms. Waves rise softly and settle again beneath the quiet pull of the moon. Far from shore, long swells travel through cold water without sound or hurry. Tides continue their steady turning around distant coastlines. Sea water drifts through harbors, across reefs, and beside sleeping beaches under pale night skies. the deep ocean remains calm beneath layers of moving water. Tiny currents carry warmth and minerals through the darkness in endless silent motion. Above the sea, clouds drift slowly across the night. Moonlight stretches over the water in soft silver patterns that shift with every gentle wave. Along quiet shores, tide pools rest beneath the stars. Small ripples touch the sand and fade again into stillness. Far below the surface, the ocean floor remains cool and dark. Ancient rocks rest beneath drifting currents and slow falling marine snow. The rhythm of tides continues without stopping. Water rises softly along the coast, then slowly retreats again into the sleeping sea. And the sound of waves grows softer now. Lower and slower. Quiet and distant beneath the night air. The ocean keeps moving calmly through the darkness. Endless water beneath endless sky. Slow tides. Cool air. Soft waves. Deep water. Silent currents. Quiet moonlight. Still horizons. Gentle drifting sleep.